We've talked about resistors and capacitors, and then we put them together for RC circuits. So named because they have resistors and capacitors. Physicists aren't going to imagine it as a lot, as you can see. There's really only one other thing to chat about, and it's really, we've already kind of done this work. You had an expression for the charge appearing on a capacitor as a function of time. This is a charging capacitor equal to C1 minus e to the minus t over tau. And what is tau? Characteristic time. How do you calculate it? RC, right. So, of course, that is, if you have a circuit with multiple capacitors, multiple resistors, that you can simplify using the same technique we've been simplifying. This R is the equivalent resistance of the whole circuit. C is the equivalent capacitance of the whole circuit. So you might have a capacitor bank and it's in an arrangement of resistors. You do all the work there. You pare it down into one equivalent resistor, one equivalent capacitor. That's your time, your characteristic time, your RC, which we just abbreviate as tau. Tau. So this is the charge as a function of time on a charging capacitor. We also have an expression for a discharging capacitor, usually written like this, so this is how your book writes it at least. Where Q is the full charge of the capacitor, it's what you're starting off with. I should point out, just from the definition of capacitance, that's the same thing, right? The definition of capacitance, I'll write that here too. Charge per unit voltage. If you solve that for charge, you get capacitance times voltage, and that's here, right? Our voltage is being played by script E. We'll talk about where that comes from and how it's different than voltage in just a few minutes. So we have these two expressions, and I also give you an expression, at least for the charging one, for the current as a function of time. What I want to convince you of is, if you have these two expressions, you don't need those. Because we can do this. We can remember the definition of current. What is it, by the way?
Voltage over resistance.
So you're thinking of Ohm's law. That is true. It is voltage over resistance. But that's not the definition. You said it over here. I want to look for the mathematical definition. Time derivative of the change in charge. Alright, dq dt. So let's do that here. Let's take a derivative, time derivative of the first one. Right? So the capacitance and the EMF are constants. The capacitance is the rated capacitance of the capacitor. The EMF is from the battery. Those are constant terms. They're going to come out. I'm left with a subtractive construction. So 1 is a constant. Derivative of a constant is. So that's not going to appear, right? So the only thing I have to worry about is CE times the derivative of e to the some stuff, right? The derivative of e to some stuff is e to the stuff times the derivative of the stuff, right? That's how that works. So I get here CE. I've got a negative here, put that here. E to the some e to the stuff times the derivative of the stuff, that's minus 1 over tau with respect to time. The negatives are going to go away. I've got a tau coming in the denominator, which is equal to CE over tau, e to the minus t over tau. But tau itself is what? What's the time constant? RC. Right? I lose that. And I get E over R, e to the minus t over tau, which if you look on your formula sheet is what you have. Right? Notice I think it was Garrett who gave us the definition of current as voltage divided by resistance. That's right here. This is just Ohm's law, but it's Ohm's law for a changing current, right? Specifically changing in this way. This exponential function provides what a mathematician would call an envelope to this, right? Here is your relationship. I is equal to E over R, enveloped by this function, the decaying exponential, right? So the whole point is, remembering this definition of current gets you a lot of places. This formula is on your formula sheet, no big deal. But if you need it, you can always derive it. If you know the charge, specifically if you know the charge as a function of time, you can always get the current. You can go the other way, you can integrate this to get the charge. That's a little bit sketchier. We don't usually do that in this class because you've got definite integrals to deal with, and so you need to know your what you call your boundary condition, your initial condition, final condition. You might not know those. So it's a little harder to go that route, but if you have the charge, you can also always get the current. You can do the same thing, of course, with the charging capacitor. Can I erase this stuff? I'll get the board. All right. If I do the same thing for a discharging capacitor, I should say, right? Take a derivative of that one. I get, well, again, I have that constant Q. That's a constant because that's the total charge of the capacitor. It's not the charge at some particular time. It's when the capacitor is fully charged. So it comes out. And then I have just the derivative of E and some stuff. I'm going to get negative Q over tau. Let me write that a little cleaner. E to the minus T over tau. All right, let's unpack some terms here. The total charge is given by CE from that other expression. That might be helpful if I put that in. And then tau is still RC. As I again lose the C's, E over R, E to the minus T over tau, which is almost the same thing as I got a while ago. What's the difference? The sign. Anybody take a stab at explaining that? Imagine you're the charge flowing onto the capacitor. And then imagine the capacitor discharges and you flow away from the capacitor. What's changed from your perspective? The direction, yeah. Negative signs in physics always tell you directions. It might not be an obvious direction, but in this case it is, yeah. Yeah, the negative sign is just an indication to you that the current's flowing the other way. That's interesting. We're not really treating current as a vector. It is a vector, or if you treat it such. But in this case, that the directional nature just kind of comes out in the wash. Usually you wouldn't care about the negative sign, because usually when I'm asking you for a current, all you care about is the magnitude, this many amps, right? And you're going to answer it similar that you would to a distance. And so if you're actually calculating, a distance doesn't care about the direction, right? If you're actually calculating a number here, you'd probably just throw away the negative sign, and that's fine. But I want you to see it and kind of think about what it means. When you're charging a capacitor, current is flowing one way. When the capacitor discharges, it flows the other way. It's like a battery wired up in reverse, right? It's charging due to the battery that's there. But then when you discharge it, the current goes the other way. Okay, questions on any of that? All right, one last thing to talk about. And that is this EMF thing, and why we use the script E as opposed to a V. First thing to talk about is that EMF stands for something which I will tell you, but we don't really talk about, right? We don't talk about it because it's wrong. But we keep it named that for historical reasons. So EMF stands for electromotive force. So here's what happened when people were investigating this stuff in the late 1800s. Late 1800s. They realized that when you had this thing, which in our language we would say provided a potential difference across two terminals. They didn't have the language yet. But they knew they had this thing that acted like what we would call a battery. And when when they hooked wires across it, things moved. We know now that this charge is moving. So they're like, well, things are moving, there must be a force, right? That's not exactly true. You don't have to have a force to have things moving. But they realized that there was a force that is in play, and that's true. Charges don't begin to move without a force, because that beginning to move is an acceleration. You gotta have an acceleration. You have to have a force if you're gonna have an acceleration. Newton's second law told us that. So they realized that there was a force, and they called this thing the force. Turns out it's not. This is actually the voltage. There is a force, but you have to look at it from the field perspective to see that, right? Electric fields produce forces. Voltages produce potential energy. So it's the same problem, just two different ways of looking at it. They got a little mixed up. I mean, they did much better than I would have done. Let's go put that out there. But they called it an electromotive force. It's not a force, which is why we don't ever say that, except for this, right now in this class, to tell you that it's wrong, right? That's what EMF means, though, right? We just call it an EMF because we don't want to say the word force. All right. Why is this different than, let's say, a voltage? Why do I write E under a battery? Well, turns out a battery, being an electrical component, has what we call internal resistance. So we usually write a battery like this. But if I were to go inside the battery, I would have something maybe that looked like this. I'm going to actually draw the battery here. I would have something that works like an idealized EMF and then an internal resistor. Again, I'm idealizing everything. Where this EMF is going to be provided by the chemical action of the battery. But anytime you have a physical component that's not a superconductor, you have resistance. Right? So this would be like some super clean, pristine voltage. And then you have this little resistance R. So, using what we learned from Kirchhoff's laws, we can kind of think about this as the total EMF. That is to say, well, okay, before I write that, let me define what we're going to call EMF. If I measure the voltage across the two battery terminals, I get a value, right? That value is different than the internal voltage supplied by the chemical action of the battery. It has gone down a little bit because there's a voltage drop across the internal resistance, right? Usually we don't care about what happens inside the battery. What we care about as engineers who are building a circuit is what the battery provides, and that's the terminal voltage, also called the EMF. But if you decide to become a battery engineer at some point, like our lab manager was for a long time, you care about this, right? You care about the fact that there's internal resistance here, and the chemical potential is different than the terminal voltage. So basically what we say is the EMF is going to equal to this idealized internal potential minus IR, where you're going to recognize, hopefully, IR as the voltage drop across that internal resistance. Again, not something we normally care about in everyday life, but in a physics class we should at least mention it. I wrote the I lowercase, which is your book's shorthand for a changing value. This changes because, turns out, the internal resistance of the battery also changes with time. This is why when you have a flashlight that is, the battery is dying, the light gets dimmer and dimmer and dimmer instead of just shutting off completely, right? If the battery provides a consistent voltage, you'd expect your light to shine exactly the same until it didn't have the power anymore and it just shuts off. That's not what happens. The light gets dimmer, right? Dimmer and dimmer. Your car headlights do the same thing if your battery's dying. That's because it's not just that the voltage is changing, the current is changing because the resistance is changing. It changes with the age of the battery. If you have a rechargeable battery, it changes based on how many times you charge it. It's got a characteristic called hysteresis, which means it doesn't actually get back to the same physical parameters after you charge it than it was before you charged it, even if, aside from the charging, the chemical structure is different in a battery after you charge it. So over time, that's why rechargeable batteries don't last forever. You have to have them replaced. It's why normal batteries drain instead of just shutting off. There's all this internal resistance. That's all I'm going to say about it. I don't do a whole lot with internal resistance, but I want you to know that it's there and that it changes, which is why the battery profile changes over its lifetime. And also to let you know why we use a different symbol for a potential. We're talking about a battery. Right? If I were to plug this in the wall, I wouldn't use this symbol. This is usually reserved specifically for EMFs that are going to change. We'll use it for other things as well. But for now, just if I see an EMF, it is a voltage, right? It's absolutely voltage. But that's why we don't usually use the V. Now, if you see a diagram somewhere with a V instead of an E, is that wrong? No. It's just, it's a convention we've adopted. I want you to see why. Any questions about any of that? All right, well, that will conclude this chapter. And also conclude the material that will be on your exam. Everything I say after this will be on next week's exam. So any questions at all about resistors, capacitors, parallel series arrangements, resistors and capacitors together, any of the stuff you've done? All right. Well, if you think of one, just stop me. Okay, now we're going to move into the section of the class where we're going to discuss magnetic phenomena. So we've talked about electricity, we've talked about how electricity works in some simple circuits, DC circuits, I should point out. We're not doing AC in this class. Now let's talk about magnetism, which seems to be an unrelated phenomenon, but we're going to find out is actually the flip side of electricity. They're actually very, very, very closely related. So let's go back just a step and get some vocabulary out of the way. If this is an electrical charge, there's nothing wrong with putting just one of them up here. And we did this when I was doing the field lines. We showed you what the field lines look like for a positive charge. We talked about field lines for negative charges. At some point, I drew another charge up here, but for just a second, let's get the language out of the way. We call this a charge. An older way to talk about this would be say that it's a pole. Pole is sort of a workhorse word for us in physics. It used to be used a lot more than it is today. Crude definition, it's an instance of a particular quality that we're talking about. We can talk about mass as some sort of gravitational pull. We wouldn't, but you could. A charge would be an electrical pole. Electricity has two kinds of these, right? We have a positive and a negative. But it is absolutely fine for just one positive charge to be around or one negative charge to be around. If there's just one of them, we call it a monopole, one pole, right? So a single charge is an electrical monopole. If I put more of them in, I can change the language. At some point I drew this up here, right? I gave you a negative charge. And I said, at least if I remember correctly, I said, we'll assume that this is the same amount of charge, just different sign. If that's the case, you get fields that look like this. If I have the same amount of charge, just different sign, I call that particular arrangement an electrical dipole. So I'm not saying that this whole thing is a monopole, I'm saying monopole is the word we're talking about. If I put two of them there, opposite sign, I've got an electrical dipole. You can go farther, you can have quadrupoles and octopoles and whatever you want to have. But we have an electrical dipole, and I probably said, because I usually do, that when you saw the field lines, I said this probably looks similar to something you saw in 5th grade science when your teacher sprinkled some iron filings on a piece of paper and held a bar magnet underneath it. And those iron filings arranged themselves over what we can now say is the magnetic field. They line themselves up with the magnetic field lines, and it looks a lot like this. But we start here because you've seen this before, and magnetic fields look similar to this. So, what does a magnetic field look like? Well, if I take this positive charge, I won't erase because I know you guys are taking it. I'll read on. If I take the positive charge and replace it with something that I will call an N pole, north pole is what I'm getting at. We don't use that language a whole lot, but it's how we've learned it. I take my negative charge and I replace it with something called a south pole, right? And don't get hung up on the names. Positive and negative are just names of different types of charges, different poles of charges. North and south are just random words that we have chosen to indicate something opposite, right? A north pole behaves in some sense oppositely to a south pole. Don't get hung up on the geographical names. They're related, but not quite the same. And then I realized that those two things are both contained in one hunk of metal. I get, at least outside of that hunk of metal, a field, a magnetic field that behaves really similarly to the electrical dipole. So we can talk about the magnetic field rules like we talked about the electrical rules. Magnetic fields begin on north poles, and at least outside of the magnet, they point towards, I'm not going to say they end on, they point towards the south pole. So I would get something actually here that would look really similar to what I got up there. Now here's the difference. Magnetic monopoles don't exist. At least we've never found one. It's actually not a theoretical, it's not something we've derived. We haven't looked at fundamental laws and, oh, it clearly shows here in these first principles that magnetic monopoles don't exist. We've just never seen one, and we've been looking. We're still looking. People are looking, right? Probably we're never going to find one. The most interesting thing that could ever happen in any of our lifetimes to physics would be somebody finds a magnetic monopole. Everything you've learned so far in this course would probably have to be rewritten. Sorry, my bad. But probably not going to happen. At least that's my opinion. Magnetic monopoles seem to not exist. So you will never find just one north pole out by itself like you might find a positive charge. Electrical monopoles are fine. Electrical dipoles are fine. Magnetic monopoles, not fine. Okay, well, why can't I just cut this bar magnet in half? That's what it is, it's a bar magnet. And you can. I can cut it in half. You don't have to write this down. I'm going to fix it in just a second. You can cut it in half, but as soon as you do that, you have a south pole appearing here and a north pole appearing here. Right? So you can cut a bar magnet in half, but then you have two bar magnets. You've doubled your amount of north poles, doubled your amount of south poles. Monopoles don't seem to exist. What happens inside the magnet then is these field lines actually come back and connect. Magnetic fields always connect to themselves. They have to bite their own tails. Electric field lines can go off to infinity, come in from infinity. Magnetic field lines cannot. Because monopoles don't exist, they always bite their own tails. We typically don't look at the fields inside the magnet when we're in 5th grade science. We just look at the field outside the magnet. But inside the magnet, they connect. Turns out they connect in nice straight lines. We'll see why later. So we know what magnets do for us, right? They attract certain types of metal. Certain types they don't, right? They attract anything with iron, mostly. They're called ferromagnetic for that reason. But they do other things, interestingly enough. Magnets turn out to be interesting things. So to see what they do, let's take a magnetic field